All right, physics. I said we were going to review. Here we are doing some review. If you were in class, if you've been in class, what I actually did was I passed out some little green books. Kind of weird. Those green books are actually things that are already you've already taken care of those. I'm just distributing stuff that already belongs to you. The green books are like the green books that you've seen in the past, right? They are old Regents exams compiled into a little compact travel size book. The nice thing about it is that they have small explanations right in the back. Um, if you're a fully remote student and you want one of the green books, send me an email. Let me know. I will leave one in the office for you so that it can be picked up. Um, if you're if you want access to the book but you don't want to come in and get the book, um, I may also be able to just post the pages. I think that I can use my CPA as an extension of the classroom. This is just a part of the classroom environment. It's something that you would have access to if you were here, so I think that I can comfortably post that on my CPA. I don't think we'll run into any like copyright legality problems there. If we do, that's a me problem, not a you problem. But let me know how you want to kind of approach that and how you want to look at it. In the meantime, what I want to do is I want to take a look at the June 2015 New York State Regents in physics, and I want to point out some stuff. If I scroll down and I look at question 1, or question 2, or 3, or 4, they should look pretty darn familiar. The reason for that is I gave them to you not long ago, right? This was part of your midterm review over the break. I wasn't kidding when I said the questions that you see are old Regents questions. The style that you see, this is how they ask it. There's only so many ways to look at this, right? You should recognize number 7 from somewhere. Um, I'd like to look at some of these questions that you haven't done, or I don't think you've done, and if we have done them, it's been a while. But the ones that I want you to look at right now, right, real quick, number 5, right here on this page. And again, I'm looking at the June 2015, right? So number 5 and number 9. Hello? Can we highlight stuff, please? Number 5 and number 9 and number 11. Right. Those are the ones that I want you to look at like right now. We'll look at a couple others in a few moments, but I figure just break this up into small chunks, right? So number 5, number 9, number 11. You should also recognize number 10. Not going to do it right now, but you should recognize it. Yeah. Number 5, number 10. Number 5, number 9, number 11. Take a few minutes, answer those questions. Pause the video, and then come right back. I'll explain them. Oh, yeah, my bad. So, let's look at number 5. So a student throws a 5 Newton ball straight up. What is the net force on the ball at its maximum height? All right. This is a very straightforward question, but be careful with it. And I only say be careful with it because you might be really tempted to pick choice 1. And I would urge you not to pick choice 1. The reason that you shouldn't pick choice 1 is that there is something that is equal to 0 when the ball is at its maximum height. It's not the force. It's velocity. It stops moving at its highest point. So its velocity is equal to 0. So what would be measured as 0 is 0 meters per second, not 0 newtons. Right? The force acting on the ball should be the force of gravity on the ball. Now that you've heard gravity, you might be very tempted to choose 4. I would again urge you not to choose 4. And the reason for that is 9.81 is the acceleration due to gravity, which we measure in meters per second squared. Not the force of gravity. The force of gravity is the weight of the ball measured in newtons. which was given to us. It's 5 newtons. And it points down, because it's a force of gravity. It points down towards the center of the Earth. So it should be choice 3. Be careful, right? Not a tricky, not a hard question, not a difficult question, but a little bit tricky, right? We've actually done number 6 as well, but we'll come back to it. We've definitely done number 7. Haven't done 8 yet, because we haven't talked about that yet. Number 9. A basketball player with a certain amount of weight jumps up from the floor towards the basket. The magnitude of the force of her feet onto the floor is this much. So what is the force of the floor back onto her feet? This sounds like the force of the feet on the floor, force of the floor on the feet. For every action, there's an equal and opposite reaction. So if we're pushing down with 1 times 10 to the third, we should push back up. Also, 1 times 10 to the third. Choice 2. Finally, number 11. Number 11 has some weird phrasing. And if you struggled with number 7, it's not a big deal. This is why I'm doing review. This is why I'm looking at the wording of these questions specifically. The Hubble telescope's orbit is really high above the Earth's surface. Telescope has a mass that's really big, and the Earth exerts a gravitational force that's also really big. The magnitude of Earth's gravitational field strength. At this point, what I would encourage you to do is look at your reference table, go to the very back page, right? Go to that equations sheet, and look on the right-hand column, and look for lowercase g. Lowercase g is listed as the acceleration due to gravity, or the gravitational field strength. And we actually have an equation for lowercase g in the left-hand column. It's lowercase g equals the force of gravity, F, over m, the mass. Normally, near the Earth's surface, the acceleration due to gravity is 9.81 meters per second squared down. However, I want you to look at this number here. 5.6 times 10 to the 5th meters. We're really high above the Earth's surface. We are orbiting Earth. We are high enough that the acceleration due to gravity isn't 9.81 anymore. We're trying to find out what it is. So we need to use the gravitational force from the question and the mass from the question to find choice 3. 9.1 times 10 to the 4th divided by 1.1 times 10 to the 4th is equal to 8.3. Right? The gravitational field strength, the acceleration due to gravity, will change as you get further away from Earth. It's going to get smaller because you're further away from Earth. That's like how space works, right? That's why rockets have to use a lot of force to get away from Earth, and as they get further away from Earth, they don't have to use nearly as much fuel because they're not fighting that acceleration due to gravity anymore. Right? So it should be 8.3 newtons per kilogram, which is the same as 8.3 meters per second squared. Right? Now, the next piece, the next couple questions that I want you to look at are 15 and where was it? There's one more question. Oh, you should recognize 22. Maybe it wasn't 15. Well, you know what? I definitely want you to look at 15. Look at 15 while I figure out the next question, because there was another question here that I definitely looked at. It's none of those guys. You should recognize 33. Oh, it was 41. So 15 up here and 41, right? Those two also. So take a look at those. You're back. Okay. 15, again, phrasing, right? So a block slides across a rough horizontal tabletop, and as it comes to rest, there is an increase in. Right? It is a horizontal tabletop. So I cannot have an increase in gravitational potential energy, because we're not going up. That's the only way that can increase. I cannot have an increase in elastic potential energy, because it doesn't say I'm compressing or stretching anything. There's no spring involved. I really hope that I muted that, otherwise I'm so sorry that I just like coughed into your ears. It's sliding and coming to rest, so it cannot have an increase in kinetic energy. The only thing that remains is thermal energy, heat, internal energy. And the reason it increases, they use the word rough, and rough implies that there's friction. And when there's friction, typically when two surfaces that have friction between each other rub past each other, you make heat. So internal energy is what goes up. All right. Now question 41 is the other one that I wanted to look at. And then, again, we'll do some more review in the next few days, but I don't want to overkill this. I want you to have resources with which to study. The Regents are a good place. If you like that little green book, one of the other nice things about the green book is that it separates at the very end, very last page of it, separates things by topic. The topic that we've covered so far, the single topic, is mechanics, right? If you look at the topics on my CBA, it's classical mechanics. That's the only topic we have because it's just such a broad thing, right? It's actually a lot of like what would be first semester physics in college. But anyway, take a look at 41 here. So 41 is an object is in equilibrium. That means something very specific. It means that all the forces acting on the object cancel each other out. They all add up to equal 0. And they call this a force vector diagram, which is just a free body diagram. These are all the forces that are acting on an object. So which one could represent the forces? Well, it can't be one. That's a single unbalanced force. It can't be two, because even though there are two forces, and they are opposite, they are not equals. So they cannot cancel each other out. It cannot be number 3, because even though there are two forces that are equal and opposite and therefore cancel out, there is a single force with no opposite that cannot cancel out. It must be choice number 4 because these two arrows can be separated into sideways and up and up. The sideways portions cancel each other out. The two portions that go up will be exactly enough to cancel that single big arrow that points down. And therefore these forces are actually in equilibrium with each other because they will all cancel each other out. All right, this is an equilibrium question. This is a forces question. This is a components question. This is a really, really good encompassing question for several topics that I like. All right. Now, like I said, we will get some more review in. If you are fully remote and you would like a little green book, please send me an email. Please let me know. I will leave a copy in the office for you. It'll have your name on it and everything. It'll have like a sticky note with your name on it, so you can do whatever you want with it. But if you just want like the pages, I can post those. I can probably post those. I will do my best to make sure that I get that done. Keep an eye out for a little more review. Remember that the power lab, right, the stairs lab, is due on Tuesday. That is the... what date is that? Tuesday, the 19th. So just don't forget about that. And if you have questions, if you have comments, if you have things that you want to ask about, please let me know. Send me an email, carrier pigeon, smoke signal, something. Find some way to communicate with me. Otherwise, I'm going to figure that everything is going just fine, all right? If you don't tell me something is wrong, I'm not going to know something is wrong. So please tell me, right? I won't bite. I'm not going to yell at you or anything. It's not worth it. We're all here, right? So I'll do my best to be accommodating. In the meantime, be good, stay safe, stay sane, and until the next time in class or in the next video, take care of yourselves. See you, kids.